So the determinant will never be negative, for example. You can't have negative information. At the worst it will be 0. The idea is to design your data in such a way that x dash x inverse ka determinant is maximized. Okay? How will you maximize the information? By increasing variance of x1. Because ultimately what is the determinant? Determinant is summation xi minus x bar square. So the determinant is essentially a determinant here is. So how do you maximize the information? In this case, yeah, this is it. So you must maximize this quantity. You must minimize this quantity. When will you maximize this quantity? When this quantity is as high or this quantity is as high? But maximizing x1 as square is equivalent to maximizing the variance of x. Right? Maximizing x2 as square is equivalent to maximizing the variance of x2. So when you collect your data, please make sure that the data on each individual variable has as much variance as possible, but the covariance between the two must be as low as possible. That's a very, very important thing to do when you are designing a regression model, because later on you will see when you do tests of significance and things like that, this will actually mislead you quite a lot in terms of hypothesis testing. Okay, so that's the determinant, right? Okay, so coming back to our matrix, we have done the determinant. So we have we are trying to find the inverse of that. Okay. For the inverse, first you have to find the determinant. We have to ensure the determinant is not 0. You know now when the determinant will not be 0. Right? When there is some information in the data. Let's assume we have done things properly so that there is some information in the data. Right? Okay. And then, if you have no information in the data, your computer will not tell you there is no information in the data. It will say matrix inversion failed. It will say x dash x failed. I can't invert x dash x. That's what it will say. But unless you know what it means, yeah. So what will you do if you find your x dash x inverse? Your computer tells you that x dash x inverse does matrix inversion fail. What will you then do? So you will find some more data. You will add some x. So you'll go to some more households. You'll find households where x1 and x2 are not perfectly correlated, and then you will add them to your data. Yeah, then you will add those households to your data. Right? So that's where you will be able to do that regression.
So the variance of x1 and x2 has to be maximized.
Yeah.
And the covariance of x1 and x2 should be minimized.
Yeah.
But isn't that always the case? Like if variance of x1 is as high the variance, is that the case always, or should be negative the case?
Meaning?
Meaning that are they related?
No. Higher covariance does not mean higher variance of x1 and x2 does not necessarily always mean that the covariance between x1 and x2 is minimized. They can be very highly correlated, no? If the variables are perfectly correlated, then larger is x1 square into x2 square, larger will be the covariance x square. Because they will be equal, because because the determinant will be 0. So in which case there is no guarantee really. So that is something that you as a practitioner have to ensure. As somebody who is actually trying to design a regression model. See, regression models have to be developed in your head. They don't get developed on computers. Computers only run them. Okay, and computers will, if you put junk in, junk out will come out. Yeah, I was once doing some consultancy work for a very large oil major. And what they wanted to do was, they wanted to predict how the two-wheelers situation would be all over the world. So for each country, we were regressing that country's two-wheeler population, that country's GDP. And very often I found that maybe the number of two-wheelers in Argentina were much more correlated with the GDP in Australia rather than that in Argentina itself. Right? All these are essentially data problems. Right. So I can't go on the computer and say, because the computer has told me that, to know how many two-wheelers there will be in Argentina 20 years later, you must predict what the GDP in Australia will be 20 years later. I simply can't do that. That's just junk going in and junk coming out. Right. So you have to think properly around your problems. Okay. Another thing, yeah. Can you not drop one of the variables? That's an important question she asked. What will happen if you drop a variable? If your variable that you're dropping is correlated with the error term that you have done, then you can't have it, then there will be an omitted variable bias. Right? No, but then the problem is your regression will run, but the beta hat that you will get will neither be unbiased nor consistent. So the problem is it will not have much to do with the actual beta that you are trying to estimate. So you will really be throwing the baby out with the bathwater. Okay? So that's something that you should not necessarily do. Okay, unless you're sure. See, typical cases, but that's something that one is very often tempted to do. And one of the indicators that when you do this, something going wrong is when you drop a variable, the sign and the coefficient of the retained variables change dramatically. Right, so beta 1 could be 0.3 when you include x2. If you drop x2, it might become 27 and become minus. Those rapid changes indicate that there is something wrong. Right, when you drop variables. Yes, so dropping variables should be done with a great deal of care. Okay, right, that can't be a generalized solution. In fact, there are no generalized solutions to regression model. They are all essentially, all that I can teach you is ways of thinking around problems, not ready-made solutions to those problems, because they don't really exist out there. Okay, so this is x dash x. Now another important point I wanted to show you was, so what is determinant of x dash x? I got those things by dividing by n square. So I should actually put an n square out here and then say variance of x2 minus yeah. I want to maximize the determinant of x dash x. So another way of maximizing is to change n, increase n. But when you increase n, what are you doing? You are getting more data. That is, you are getting more information into the system. Right? Therefore, determinant of x dash x is very clearly a measure of the information in the system. Right? So determinant of x dash x is a very, very important quantity. Later on, when you do a little bit more statistics, you realize it's actually what called the Fisher information. Yeah. No, there is nothing called how much. With 0, you have a problem. The larger determinant, the better. So when you make it as large as possible, when your n is as large as possible, so you've collected as much data as you can when the variance of x1 and variance of x2 are maximized, okay, and when the covariance of x1 and x2 is minimized. Right. Now these are questions which you have to, therefore, these are numbers which you have to look at before you start collecting the data. So what will make a good regression model? A model which has as much data points as possible. So the important question is, can I get more data? That must be your first question. So your limit should be, to n should be given by your time and money that you have. As much data as you can is the first question. What kind of data to collect? The data to collect must have as much variation x, x1 and x2 as possible, but as little correlation between x1 and x2 as possible. That's how you must design your surveys. Right? So what this tells you is, this gives you a guideline about how will you actually go about collecting data, collecting information. Right? Therefore, this is a very important quantity to remember when you do a multiple linear regression model. Right? Okay, so now, so suppose you've got this. Everybody's written these numbers here. So now suppose you've got this determinant, right? Suppose this determinant is not 0. Okay, I will write this as not 0. There is some invertibility. Okay. Now what? How do I find the determinant? How do I invert this? I go this comes here, right? That matrix of cofactors and principal minors, etc. You know that, right? So let me find that matrix of cofactors. The first quantity is summation x2i square. That will be a positive quantity. Right, I cancel first row, first column, whatever remains. First row, first column, 1 plus 1 is 2, 2 is an even number. So what remains gets just a positive sign. That's how you learn to invert a matrix, right? Although you have not learned to invert a matrix, go and look at Google. It tells you some very easily how to invert a 3 by 3 or a 2 by 2 matrix. Right, I am just leaving it at a 2 by 2 matrix. Right, but the general principles hold everywhere. Okay? x2 square. Then if I took this out, what will I get? Minus, right? Then this and this, right? Yeah? And then finally, then this whole thing has to be divided by this is x dash x inverse. Yeah? Everybody gets why this is x dash x inverse? Okay? This is x dash x inverse. Now, so let me write this a little bit more carefully. This is why is the first term like this? Because what did I do? I divided the whole thing by n square. Then I said summation x2i square, right? Summation x2i square upon n will give me the variance of it. So I have divided the numerator and the denominator both by n. So this n square has become n now. Right? This n square has now become n. Why has this n square become n? Because this has become, I have written n here actually. So divided both by n. Ordinarily what I would have got? I would have got this quantity divided by this whole thing. I divided this by n, so I have got this. Right? Then what do I get? Again, yeah? The same quantity here. Yeah? And what will come here? Variance of upon this whole quantity
can you please explain again how n came in?
See, there's an n square here. If I ordinarily what would have got, by dividing this, I would have got summation x2i square upon this n square into something. But x2i square upon n is nothing but the variance of x2. Right, so I divided this by n, this by n. Right? So this is now my x dash x. Yeah? This x dash x has to be multiplied by x dash y to get my beta 1 hat, beta 2 hat. What is my x dash y? Summation xi yi into summation yi, right? This into, yeah? Alright, just to sort of help you see that a bit. Yeah? No, it will be clear in the video. Right, so I will write this as yeah? Now is it clear? It's clear here, no? Right. So now, so as long as you get to see that, we can come back to our original board because I'm going to do the calculation there. So first row into the first column will be beta 1 hat and beta 2 hat, right? This whole thing is supposed to be equal to right? So we have beta 1 hat is given by, so this, so how do you do this minus this? So this is a 2 cross 2 matrix, that's a 2 cross 1 matrix. What will be 2 cross 2 into a 2 cross 1? 2 cross 1. 2 rows, 1 column. The first row will be beta 1 hat, the second row will be beta 2 hat. Right? The first row will be beta 1 hat, the second row will be beta 2 hat. Right? So if you did that, what will you get? You get summation xi yi, right, into variance of x2 upon n. Now remember, okay, if I divide this by n, I'll get the covariance xi yi, right? So I will write this as covariance x1i yi. N will now go completely, right? Because I am dividing numerator by n. Minus summation xi square. Again I will divide by n. So what do I get? Variance of x1i our x dash y matrix has to be thought of more carefully. No, we have not got the x dash y matrix correctly. Right? Because your x dash y matrix actually will be, your x dash x is like this, no? So it has to be like this, sorry. x dash matrix. So x dash y will be really this into summation x1i yi. Yeah? Alright? Just to make it there clear. You can zoom in and see, right? x1i yi, x2i yi. Yeah? So, our matrix will be beta 1 beta hat. Beta 1 hat will then be so it would be beta 1 hat would be variance of x2 covariance x1 y1, this quantity into this quantity, right, minus covariance of x2y, the whole thing divided by yeah, because what have I done? I've been a little bit smart. First I kept it this is unusual, yeah, but I've kept it like this. So first summation xi y ऐसा ही रखा, right? Summation x2y ऐसे ही रखा, नीचे n square common है, फिर दोनों को ऊपर से n से divide किया, तो फिर summation x2 y became covariance x2 y2, right? So beta hat को क्या मिला? Beta hat will be variance of x2 covariance x1 y1 minus covariance x2y into covariance x1 y1. So covariance x1 y1 को आप x1 x2 upon this. See, this into this. इसको डिवाइड करेंगे n से तो क्या होगा? Covariance xy, x1 y1, x1 y, right? Covariance x1 y, a covariance x1 y minus covariance x1 x2 into summation x2 y. x2 y को n से डिवाइड करेंगे तो covariance x2 y, right? Covariance x2 y upon covariance x1 x2 as it is. Sure? The whole divided by variance x1 variance x2 minus covariance x1 x2 whole square, right? ये beta 1 hat आ गया. Sure? What will be beta 2 hat? So this into this. So minus first. Plus yeah. So that will be, there's a minus there. So you get beta 1 hat, beta 2 hat, right? So if you, it's very easy really. This is plus. So if you actually write this way, it is variance x1 into covariance x2y, where this was variance x2 into covariance x1y. So x1 and x2 just get interchanged. Right, minus covariance x2y के जगह covariance x1y, covariance x1 x2, right? Okay, we are going to use this formula quite interestingly later on. Okay, because look at this friend, covariance x1 x2 Right? I'm going to break this formula down into something useful later on. Right? So is this idea beta 1 and beta 2 hat कैसे आता है? And for you understand how it will be in a more general linear regression, we'll not solve it here. Right? But in general, x dash x inverse x dash y. And what will always remain critical is the determinant of x dash x. Okay? Right? So that's how multiple linear regression happens. This is about estimation of parameters. Now, because each parameter is a random variable that we'll estimate, we'll have a probability distribution. So it's very important now to understand what the properties of those probability distributions are and to learn what are called hypothesis tests. Right? So we have to learn things about the t-test and the z-test and the chi-square and the f distribution, all that, which we will do from the next class. Right? So do you have any Yeah, so suppose x1, x2 are highly correlated, and if you drop x2, then what's going to happen? The new regression equation, error term is going to contain x2, but x2 and x1 are correlated, so beta will be neither consistent nor unbiased. We have seen that in our daily. So you can't drop a variable. So typically what will happen is, the coefficient of x1 which you are getting earlier and the coefficient of x1 which you will get later will change dramatically. And that's a sure sign that there is a problem with your dropping of variable. Right? So thank you folks for listening to me carefully.